Hello, I am Alireza Lotfi Takami, and I'm going to present RIDE, Energy Efficient Data Allocation on Compound Racetrack-SRAM Scratchpad Memory for Real-Time Embedded Systems. First, I'm gonna have an introduction, then I'm gonna talk about related works. After that, I'm gonna talk about and explain preliminary, then a motivational example, then I'm gonna explain our hardware-software co-design approach, and at the end, experimental results and conclusion. Real-time systems have some features and properties. They have energy constraint. That's because the source of energy of most of embedded systems are battery, and most of embedded systems are real-time. It means they need to finish their tasks in a specific deadline. Most of embedded systems are reactive. It means most of the time they are in idle mode, waiting for an event, then respond to that event in a specific time frame. Memory is very important in embedded systems because about 20 to 50% of total energy consumption of embedded systems is related to memory, and memory also has a considerable part of execution time of a program. In general purpose systems, cache is used as on-chip memories. Because cache is hardware controlled, its energy consumption is high, and also it's not area efficient, and the access time to cache is not predictable. Because of these reasons, we use SPM as on-chip memory in embedded systems. SPM is a software controlled on-chip memory, and because of that its energy consumption is lower than cache, and it's area efficient, and it's predictable. As SPM is software controlled on-chip memory, we need some data management method. And this method are static allocation method and dynamic allocation method, and we can do the data allocation on SPM using we can have different type of allocation. We can have integer linear programming or dynamic programming to find optimal solutions, or we can use, but this type of optimal algorithm take too long, and because of that we use some heuristic algorithm for data placement and data allocation algorithm on SPM. Here we can see a classification of related works. We can classify related works in two major parts: on-chip, the works, some of them which work on-chip memory, and some of them which work on off-chip memory. Some of them focus on using NVM as part of on-chip memory. Some of them don't use NVM. We can also classify them about their target embedded systems. Some of them work on single core embedded systems, some of them multi-core embedded systems, and they also have a static or dynamic allocation, or they focus on code allocation or data allocation. Here you can see another classification of related works, and this table shows that if they are working on execution time of program on embedded systems, worst case execution time, static energy consumption of embedded system, or dynamic energy consumption of it. We are going to propose a new architecture for embedded for on-chip memory, and in this architecture we use a new type of memory. This new type of memory is RTM. You can see the cell of RTM memory here. It consists of a tab and a tape and some domains on this tape. As you can see, there are some transistors for access port to read and write data on a domain of racetrack memory, and you can also see some shift transistors, and so this in this type of memory we need shift transistors and shift operation to access data. We can use a lot of access port on each tape, and if we use more access port on a tape, we can access each data faster, but it's not faster and with less number of shift operations, but it's not memory area efficient. Or we can use only one access port, but we need a lot of number of shift operation to access each data, but it's area efficient. Here you can see memory parameters of different type of memories. As it can be seen, there are memory parameter of RTM is considerable. It's comparable with other memories, but it has shift operations, so we have shift latency and shift energy consumption in RTM. So we need to decrease number of shifts when we use this type of memory. Here we have a motivational example. In this motivational example, we have a trace of memory access, and here you can see each place of memory, how many reads, how many writes, and the total number of access to each address of memory or each place of memory. We use three different type of memory architecture. The first one is pure RTM, and we have in this type of memory architecture, to access this sequence of memory addresses, we need 67 shift operation. We can have a pure SRAM architecture, and we also have a hybrid SRAM RTM memory architecture, and we try to put the allocate address with the total with the most number of writes in SRAM and the other data on RTM, and we put the data with most access on the middle of each tab to decrease number of shifts. In this architecture, the total number of shifts is 37. As it can be seen, this hybrid memory architecture, SRAM consists of SRAM and RTM, can improve execution time and energy consumption of embedded system comparing with pure SRAM architecture or pure RTM architecture. In our on-chip memory architecture, we use this cell, RTM cell, consists of 8 access port and the total number of domains on the tape is 32. So the maximum number of shifts to access a byte of data is 3, and the minimum number of shifts is 0. And most of our on-chip memory architecture consists of RTM, and we also have a little part of our on-chip memory is SRAM. Here you can see the formula that we use to calculate or measure execution time, dynamic energy consumption, or static energy consumption of our memory architecture. And we used a heuristic data allocation algorithm. In this data allocation algorithm, the input is size of SRAM, size of RTM, and number of tapes, and the first position of access ports. And at first we sort the data according to descending number of writes, and we put the data with the most number of writes in SRAM. Then we sort the data according to memory access, and we put the data with the most memory access in the second and third position of racetrack in each tab, and the other data on the first and the last position of a tape. Here you can see the tool chain of our tool chain. The input is a program and also memory parameters that we used NVSIM to find out the memory parameters, and we used our GCC compiler to create executable file of our program, and we used simple scaler to create memory trace. And using this memory trace and memory parameters as input of our simulator, and we use our simulator to simulate on-chip memory architecture and the data allocation algorithm. The output of this simulator is energy and execution time of program. There is also another output that is memory access time for each on-chip memory architecture. We use this one as and also the executable file of program as inputs of Ottawa. Ottawa is a tool that we use to calculate the worst case execution time of program, and we have the output of Ottawa is worst case execution time report. As it can be seen, our approach has considerable improvement in energy consumption of embedded systems comparing to SRAM, STT-RAM, or pure RTM or pure SRAM on-chip memory. It also has considerable improvement in execution time comparing with other on-chip memory architecture. We suggested a new hybrid SRAM RTM on-chip memory architecture. Using our heuristic data allocation algorithm, we reduced the total number of shifts comparing to pure RTM architecture 94.5%, and comparing with SRAM STT-RAM on-chip memory, we reduced energy consumption about 62.8%, and the execution time about 62.5%. But in our approach, the worst case execution time is on average 1% higher than pure SRAM memory architecture. Thank you for your attention.